Section 2.1, we are going to talk about the definition of the limit. The limit is a number L is the limit of a function f at a point A if, given epsilon bigger than 0, there exists delta such that as long as x is within delta of A but is not A itself, then f of x is within epsilon of L, the limit. Then we call this the limit of f. Now you notice that x cannot be A. That is, we only care about the delta neighborhood of A, what is close around the house. We don't care about the house itself. The limit is the concept of looking at everything around, very, very close, the closely around that number, but not the number itself, and see what happens with the function f. Now that is a very unusual concept that hasn't been encountered in mathematics until calculus. Why would we care about what's around it but not the thing itself? Because sometimes what's around it is all we can handle. Well, the thing itself is unmanageable. So if as long as we can manage what's around it, that's all we care about. And it's a very new concept, so a lot of people might find it hard to grasp at first. But once you get used to it, it's no different than any other mathematical concept. The best way to understand this is to sit down and think about the sentence in your book for about half an hour or an hour until your brain kind of get used to it. Now to explain that now is we can consider, for example, that here's A, okay, and here A is around A, we build a neighborhood called delta, okay, this is a delta neighborhood, and anything in X is inside this delta neighborhood. And remember, we do not want X to be on A. We don't care about A itself when it comes to limits. We only care about what's around it. And then if X is in this delta neighborhood, and delta is very, very small, then over here in L, around L, we draw a epsilon neighborhood like this. Okay, this is epsilon, and then f, the function f will shift the x right in here. Okay, this is f of x. Now, if this relationship happens for every delta inside, for every x inside the delta neighborhood, and for every epsilon that is given, no matter how small we choose the epsilon, so that is, if we choose extremely small epsilon, and then look over here, you can always find the delta as long as it's small enough, it's close to A, where everything in this neighborhood, everything, okay, as long as small enough, everything in here will land through F right inside the L neighborhood. And then that's the definition of the limit. That is, the limit of f at A is called L. Again, remember, this is not about the value of f at A, but about the value around it. What is it close to? See, every value in here that's close to A will be close to L when you apply f to it. Now, as an example of this, let's consider, for example, a problem let f is equal to, so let f of x equal to, say, 2x minus 3, okay? And then what is the limit? What is the limit of, as x approach, say, 1 of f of x? Now, as x is very, very close to 1, as you say, if you imagine that something like 1.001 or 0.999, that's all close to 1. What is this thing going to be close to? Well, just by looking at it, you know that it's going to approach, when this is almost 1, this is almost 2 minus 3. So the whole thing is going to be almost negative 1, okay, depending on how close it is. And you know by intuition that the closer it is to 1, the closer this whole thing is going to be to negative 1. So in mathematical language, we say the limit of f of x as x approach 1 is equal to minus 1. However, that argument I just presented isn't good enough. We're going to present a formal argument of proof why the limit really, based on this definition, we will apply a proof to show that this limit indeed is negative 1, and we will use this particular definition as an argument. So we will prove, the proof goes like this. So the proof says, given epsilon, and remember, epsilon can be very, very small. Okay, any epsilon, you have to come up with a delta. We will show that So f of x minus L has to be less than epsilon. We have, which is 2. In our case, we have 2x minus 3 minus the limit, which is -1, less than epsilon. Okay, that's the given part. Now we have to find that delta such that this relationship stands. So what we're trying to find is x minus a, which is a is 1 in this case, is less than some kind of relationship of epsilon, and we'll call it delta if we can figure it out. Now in this equation, then it is comes out quite easily because it's an easy example. So what we do is we're driving from here. So we have solved this equation that becomes 2x minus 2 is less than epsilon, okay, which gives you x minus 1, which is what we're driving at, is less than epsilon over 2, which is what we said we're trying to drive at. We are trying to drive some kind of function of epsilon, and we will set that as delta. And therefore, the conclusion of this proof is that as long as delta is epsilon over 2, then fx minus L is going to be less than epsilon. And that concludes our formal proof. In the next section, we're going to do more examples of this kind of proof. This kind of proof is very, very difficult most of the time because it's not obvious how you might go about it, because the function in here can be really, really weird, and you have to come up with some kind of inequality. A lot of students will find this difficult, but if you do find it difficult, don't be discouraged, because this is actually the hardest part of calculus. After this, calculus will get much easier because this is only to demonstrate the principles, the concept of limits. And after this, we'll forget the concept, actually not forget it, but we'll move over the concept and actually do derivatives and integration, which is much more systematic and easier than come up with these odd proofs. However, for now, we will do a bunch of this stuff and to show you how the delta epsilon proof works. And one more last thing I want to mention is that the limit is sometimes exists, but it doesn't always exist. For example, if you have stuff inside here that's jumping all over the place, okay, no matter what you do, you can assign f of x to be, well, here, here, here. So then the limit doesn't necessarily exist. For example, a very quick example would be so-called a step function. Say if you have a function that is 0 on the negative side, okay, and then it's 1 starting at 0 and goes positive. What is this limit at 0? Then some of the x's end at 0 and some of the stuff end at 1, and therefore the limit at 0 then does not exist. Another thing is a limit, if it exists for a function, has to be unique. The reason is because of this definition, because f it has to be very close to that limit. So if you have, say, a person might argue, but what if I have a function has 2 limits because the 2 limits are very, very close? Say they are millionths of an inch next to each other. Well, then I can magnify that millionth of an inch 10 million times. Let's magnify. Okay, this is the magnified view of the 2 limits. See how then suddenly they look quite far apart. And then I will choose my epsilon. Remember, epsilon is anything you choose. I can choose my epsilon to be, say, 100th of an inch. And everything all the fx has to land in here and here, which as you can see is not possible. So if a limit exists, it of necessity must be unique. In the next video, we will work on more difficult examples of how to work the delta epsilon proof.